Okay, welcome back to the class. In this class, actually, we will see the crystalline amorphous solid, the plastic deformations, and the ways in which the plastic deformation happening in any crystal structure. So, in the previous class, we have seen the atomic densities, how we can calculate the linear density as well as the planar density. You can expect some problems there from there for university. Now here it is purely more somewhat theoretical. We can just see the concepts. Okay, we have already seen what do you mean by crystalline and an amorphous or a non-crystalline solids. Basically speaking, the crystalline solids have a regular pattern or arrangement, while crystalline or non-crystalline or amorphous particles or the objects doesn't have that regular arrangement. Okay, I'm saying more about the crystalline solid. They are firm, hold a definite and fixed shape, are rigid and incompressible. So these are the various properties that crystalline bodies or crystalline solids possess. And the particles are arranged in a repeating pattern of a three-dimensional network. Okay, like this is a two-dimensional representation. Like if we imagine a three-dimensional representation, we can see some repeating patterns or repeating units, arrangement of repeating units. So that's the peculiarity of this crystalline materials. And they generally have geometric shapes and flat faces. They already possess some specific geometric shapes and some flat faces, where these amorphous solids or some non-crystalline materials doesn't possess some that kind of thing. Some of the examples of crystalline solids are some diamonds, we can say some metals, some salts. All these things possess these crystalline structures. So on more detail, this are the crystalline and this is amorphous, and a intermediate is come, that is polycrystalline. So before going into this polycrystalline, we can see this amorphous solids. So amorphous solids are some rigid structures, but we can say some more specifically rigid like structures, but they lack a well-defined shape. Okay, they don't have a shape because they do not possess this peculiar arrangement. They do not have the geometric shape, and the variation in characteristics of solid occurs due to the arrangement of the molecules. It's all happening due to due to this arrangement of these atoms, or what we say, the molecular arrangement is not as in order as that of the crystalline. So a few examples of these amorphous solids are like gels, you can say, or the plastic which is available, various polymers, the wax, all those things are amorphous. We can say it is somewhat soft also and does not possess a particular shape, and the shape can be easily molded. Okay, so some category of materials which occurs in between or exist in between the crystalline and amorphous. So such material is known as polycrystalline material. It is also known as polycrystals. Okay, so they are the solids that composed of many crystallites of varying size and orientation. But in crystalline materials, it is arranged in a large or in a long order. But in polycrystalline material possess a crystalline nature, but for a short order, not a long term order. So that's the peculiarity of this one. So example, we can say ice and rock. So you can see if some external heat is applied, these things will lose its shape. Rock also, if we apply some external pressure, it will lose its shape and all. So these are the basic types of the materials like crystalline, polycrystalline and amorphous. So another important factor which we need to study is the orderliness. Okay, orderliness is the arrangement of atoms and molecules in solids and the liquids. Okay, how these repeating units or how it is arranged, or certain molecules or atoms, how it is arranged. So that study is, or that information is known as the orderliness. Okay, the crystalline solids have a long range order. We will call it in a short term like LRO, the long range order, which means that there is a regular pattern or a periodic arrangement of particles which repeat itself periodically over the entire crystal. So this crystalline solids, as we discussed before, possess a long range order. Okay, this repeating unit is repeating for let's say, so 1,000 or 10,000 or 1 lakh times. So it's having a long range periodic arrangement. Okay, example like a long range order, you can see the crystalline silicon dioxide, we will also call it as quartz. You can see the red atoms are silicon, and whereas the blue atom is oxygen. Okay, now coming to the other one, that is amorphous solids and liquids. They have irregular shape because that order is not long, it is short range order. Okay, now let us consider another silicon dioxide. This is amorphous silicon dioxide. This previous one is crystalline and second is amorphous. Why I have taken the same example is that if you happen to select any silicon dioxide for any specific application, first thing you need to identify that which silicon dioxide it is. Okay, sometimes it can be some crystalline, and sometimes it can be amorphous. Okay, so please have an idea of that. So this silicon dioxide, you can see that it also possesses this shape and all, but it is having a short range order, does not possess a long range order. Okay, in such arrangement, the non-periodic arrangement of particle is seen. Here a regular periodic arrangement is we can observe, but here a non-periodic arrangement, there is no order, no regular order for the arrangement. Okay, such portions are scattered, and in between the arrangement is disordered. Sometimes there can be some discontinuity happen in between, and all those factors can, or all such things can be seen in this amorphous. Whereas for crystalline, it will be uniform, periodic, and having a long range order. So the orderliness, or the information about the orderliness, is very much important. Okay, now that's all for the crystalline and amorphous part. Now let us see the deformation. Okay, this is a big topic, and we will continue it in the next class also, but as a basics we need to understand few things. Okay, the first thing is let us consider some stress strain diagram. Like strain is plotted on the x-axis, whereas stress is plotted on the y-axis. Stress is denoted by force by area, and the strain, which is the change in length to the original length. Okay, now let us see, when a force is applied, the deformation will happen, and it will go on increase, and at a certain point will be there. I will come to this point later, and it will continue like that. And the point that P is known as the elastic limit, and or the limit of proportionality. The reason is that the left side of this point, or until this point where force applied, the deformation will be elastic. Beyond this one, the deformation will be plastic. Okay, elastic in the sense that at any point between the origin and the P, if we withdraw the force, it will come back to the original shape. But beyond the point P, if we withdraw it, it will come back to original shape, but it will produce some permanent deformation. So that permanent deformation is known as plastic deformation, and the deformation which can be regained or which can be recovered is known as elastic deformation. Okay. The material is deformed beyond this point. The stress is no longer proportional to the strain, and a permanent, non-recoverable or plastic deformation occurs beyond this point P. Okay. This elastic deformation is also known as a temporary deformation, and the plastic deformation is known as permanent deformation. Okay. Both things takes place due to the adjustment or the displacement in the atomic arrangement. And we mentioned about some force which we have applied, and that applied load may be either, sometimes it can be tensile, it can be compressive, or it can be shear. Okay. Now let us see these things in a little bit in a schematic point of view. Okay. Before any loading, it will an atomic arrangements which we have seen for a crystalline material look like this, and if it is a tension, okay, tension, what will happen? This piers, you can see that it will try to elongate in either direction under tension, and the material which is in this original shape will change to this form. Okay, the linear displace or the linear dimension will increase and the lateral dimensions will reduce. In compression, just opposite thing will happen. The linear dimension will reduce and the lateral dimension will increase because the crystals are just compressed. In shear, actually a force of this kind is applied. Here you can see that the force, when it is applied, what will happen? It will shear along this direction and the deformation will be shown here. So this is a basic concept. And elastic deformation, if we say more about elastic deformation, okay, when a material is subjected to an applied force within the elastic limit, the atom within the crystals are displaced from their normal position of the equilibrium deformation. So what will happen is that these attractive forces between the atoms are there. That's the important thing which we need to consider. When a tensile force is applied, some intermolecular forces will be developed between this molecule or atoms or molecules. When compressed, a repulsive forces will be there. Okay, which we have learned earlier. Shear also, some attractive as well as some repulsive forces will be there. So these are known as the attractive forces between the atoms, balances the applied force. Here I have mentioned only the attractive force in the concept that we are doing or we are applying the tensile force. If it is compression, it will be some repulsive force and everything will be there. So such forces, intermolecular forces between, more specifically if we are saying, we can say that these intermolecular forces between the atoms balances the applied load. Okay, and the displacement of the atom is very small in case of elastic deformation, and when the applied load is removed, this will allow atom to return to their normal equilibrium position. That means these attractive forces or these intermolecular forces between the atom make these molecules to come back to their original shape, or in other terms we can say it as something reversible. That is what happening in the elastic deformation. So now let us see the Poisson's ratio. Okay, this is the Poisson's ratio. We can see some longitudinal, when we apply tensile force, some longitudinal strain will happen here, and similarly dimension is reduced in lateral, so the lateral dimensions will be reduced. So this is what happening when we exert some force. So what will happen? A Poisson's ratio is the ratio of the lateral strain to this longitudinal strain. Okay, the concept of poisonous ratio is very much important. Okay, this is, once again I will explain, this is the longitudinal strain when we apply some tensile force. Similarly, a lateral strain will be developed due to the reduction in the dimension lateral side. So this will this makes the poisonous ratio. It is the ratio of the lateral strain to the longitudinal strain. This is a negative sign because here the dimension is reducing. Okay. So now let us consider four atoms here named as P, Q, M and N, and when we apply some tensile force, what will happen is that M and N will change to M dash and N dash. That means some increase in dimension will be there in atomic level. Okay, but whereas the P and Q will the dimension in the P and Q will reduce to P dash Q dash. So this reduction in lateral dimension and this elongation in the along the longitudinal direction, that effect is known as poisonous effect. Now elastic deformation can be like this elastic deformation will end at the proportionality limit, and beyond the proportionality limit we have the yielding point will be there. We can note the ultimate tensile strength, and finally it will lead to some fracture. Okay, so we can see that we learned that beyond this proportionality limit some kind of plastic deformation happens, and this plastic deformation happens either with help of yielding or by a fracture. Fracture means it will break into two pieces. Yielding means the plastic deformation will be formed within the material. Okay, so this both things are plastic deformation. It can be either by yielding, it can be or by the fracture, whatever it is. Okay, that's a permanent deformation. Okay, both these things are permanent deformation. And in between I need to introduce you the term the brittle. Okay, for example, the glass pieces, we know it is brittle. It will break up immediately. So what is a brittle material? Here in brittle material there will be some elastic range, but the yielding will not be there. Immediately it will lead to the fracture. So such kind of material are known as brittle material. Okay, so moving to the plastic deformation, we define that like we seen that due to yielding some of the atoms move to some new equilibrium positions. Okay, as we have seen earlier, when we apply some force, the atoms will move from one position to another position. But here the atom form new bonds with the new position. That's the thing here. For attaining this thing, like a minimum amount of stress should be there. Okay, like beyond, if we give the force beyond the elastic limit, the atoms will move from one point so that it will reach the other regimes, and it will create new relationship with other atoms there. So that's what happening here. It will create new bonds at new position. Okay, hence the material is not weakened and do not return to the original position. That's what happening in case of yielding. That means the internal forces or interatomic forces or intermolecular forces will not be sufficient to balance those forces, and these atoms will move to the new position, and what will happen? And it will make new bonds. Since new bonds are made, the material, we cannot say that the material is not weakened, but its shape will change or some deformation will happen, and it will not return to the original position. So such kind of deformation we will say it as inelastic or irrecoverable. Okay, such deformation is also permanent. Okay, and this is known as a plastic deformation. Two common mechanisms in which the plastic deformations will happen is by slip and by twinning, and those things we will see in the next video. Thank you very much for your attention, and in the next video we will come with the details of slip and twinning. Once again, thank you.